Okay, so I think we're going to start the panel session. We have a remote participant. We had a little bit of a glitch getting him connected up, but things seem to be working properly now. My name is Feeney. I'm a researcher at the Swedish Institute of Computer Science at Uppsala University. And what we're discussing this afternoon with some very distinguished speakers is modeling power consumption . It's modeling power consumption in OMNeT. And the idea behind this is really, originally OMNeT was used quite a bit for wireless simulation, networks of battery-powered devices. Increasingly, people have gotten interested in the energy efficiency and sustainability of the entire telecommunications infrastructure, data centers, internet routing, wireless telecommunications, as well as battery-powered devices. So there's a much larger and broader interest in some of these topics. And so we're interested in simulating power consumption now in many different contexts. People have developed quite a lot of different frameworks. There's just a representative set in this panel. And so the question is, as INET develops, INET consolidates with both support for wired and wireless networks. Power consumption continues to be an issue for many different scenarios. Is there some way forward that can reduce duplicated effort, that can let people share knowledge more, and possibly even let people build heterogeneous network simulations? So somebody can look at how data should move between a data center and, say, caches in the internet routing infrastructure, and have some kind of common functionality that people can make use of. So we're going to have 6 very short presentations and then some discussion, which I very much hope that the audience will participate in. So each speaker is going to talk for about 5 minutes. I think we'll hold questions then until the more general discussion at the end. So one of the earliest frameworks for modeling power consumption was in OMNeT 3. It was the energy framework. I developed it in 2009. And the main goal was extensibility. The idea was that it would not be specific to any particular wireless networking framework. I used it then for mobility framework, which is a then very popular wireless networking simulation. And that actually worked out pretty well. It was quite extensible, it was pretty flexible, and then it was integrated fairly tightly into a couple of different wireless networking simulations. Integrated into MXIM by Daniel Wilcom and Carl Wessel at TU Berlin. It was presented at one of the OMNeT workshops. It was in INET, MANET, INET, so forth and so on. But it wasn't done as a framework. It just was integrated in kind of in framework-specific ways. And basically the idea was that some modules were considered devices, and those were responsible for modeling, informing the battery, informing the power source of what you were doing, of how much load you were putting on the battery. There was a battery module that modeled how the battery would discharge under load. It would eventually announce that it had failed, and then you'd have to shut down the node. And so it was I think Torsten is going to talk a little bit more in detail about how some of these sorts of models work, but this was a fairly conventional structure. So there were some good parts. You had an isolated device module that informed the battery of load, and that was usually integrated or inherited from a low-level module, such as a radio module or a sensor module. So you could have multiple devices draining power from the battery. There was also interfaces for feedback for the state of the power supply. As a battery is discharged, it is less capable of providing voltage, so that you can model the electronics interactions between a failing battery and the device. That meant that you could also model the state of failure of the whole system. You could use either the blackboard in older systems or the OMNeT signaling mechanism to inform all of the nodes associated with the device, all of the modules associated with the device that a particular device had failed. The other clever thing was that we isolated the data collection. The idea was that eventually the battery model could become fairly complicated, but users would want to collect different kinds of data from, different kinds of data from the battery, and we'd like to isolate that as much as we can, because you'd like to do visualization, different kinds of statistics collection, and you don't want to have to touch the battery because it's a kind of messy model. So, bad parts. So we had some experience. One of the big problems in the energy framework, and pretty much all of its instantiations, was that you had modules that were not battery aware or were not energy aware. There were utility models, ARP, caching, and so the host would fail. Some module, some application module, some traffic generator, some this, some that, you just wouldn't know about it, and it would just keep generating things. And the radio would stop properly, so you wouldn't be interacting with the network, but your statistics from those modules would get really messed up. So we had to play a little bit on Mixeme, but we never came to a really satisfactory solution. The other big problem is this idea of the device module, that you had some module that knew about the interfaces to the power supply. And that's really, really easy when you're modeling the radio. The radio is the last thing that the packets touch when they go out on the air. It knows what the state of the radio is. You know what the radio's state is, you know what the hardware state is. You tell the battery what the radio is doing and how much current it's draining from the battery. This is really, really hard when you're modeling a more complex system, or when you need to take into account more than just what the radio is doing. You turn on, you turn off the radio. That's the main source of power consumption, but it's certainly not the only one, especially in more complicated devices. And so now you have modules in the application and the protocols in memory. It turns out that memory caching in your smartphone can keep it from turning off, can keep the processor from sleeping, depending on what the memory caching strategies are. So you have all these more complicated effects, and it becomes much, much harder to work out who's responsible for telling the power source, who's draining things, because at the system layer, lots of different things can drain. I think this relates to some of these issues. How much time do things really take in the processor? And especially if we're thinking about more heterogeneous networks, what you'd like to do is quite different for sensor networks, for routers, for caching, for data centers. So how can we come up with some solution that handles all of that heterogeneity and still provides some consistency in the simulations? And I will hand over to Professor Torsten Braun. And I think you have, and then you should be able to see. That's
Okay, yeah, my name is Torsten Braun. I'm heading a research group on communication systems and distributed systems. And I want to share a few experiences we gained during the last years, in particular when we implemented some systems and did some investigations on energy consumption, and when we compared that with the typical modeling. So that's basically the standard way of modeling power consumption. In particular, if we have a radio module. So we have typically several states where a radio module can be, for example, receiving state, an idle state, and power saving state, for example. We measure the time and we multiply then the power with the time to get the energy and sum everything up and hope that this is correct. So this could be quite accurate, but there are also some cases where it's not so accurate, or where we might have higher requirements on accuracy. One example, a measurement example, where we measured the current in a sensor node, where a sensor just received some data and forwarded to other nodes. So in that case, the sensor node is sleeping here, receiving, then transmitting, receiving, transmitting, and so on. And what you also see here are these gaps. These might be quite important. So basically, in the first step, what we did, we tried to apply this standard state-based model. That means assigned a state to a time and did our calculations, summed up the energy in the end, and then we also compared that to real measurements. And here is a scenario where we did some measurements and estimations, which basically are done in the same way as we would do simulations. You can pick up, for example, the blue line, or the two blue lines here, which show the measured power consumption and the estimated one, so the solid line is the measured power consumption, the dash one, the estimated one, and we generate a different amount of traffic, that means we increase the traffic, and what you see here, the gap between the estimated and the measured line becomes bigger for higher traffic. So we thought about that, how can that be, and basically the answer was here. We did not model the gaps here. That means the gaps which occur when we move from one state to the other one. That means in that case, the more packets we forward, the more state transmissions, the more gaps, and the bigger is the mistake. And then we developed another model to better reflect the gaps, and applied that model, and again did some experiments and measured here the estimation errors. And the red line basically is based on the simple state model. The green line here is considering the advanced model, so we could significantly decrease the measurement or estimation error. These figures have some error rates in the order of 1 to 4%, which is pretty low. On the other side, these have already been very optimized models where we did some calibrations and estimations of parameters. So in other cases, maybe the errors might be bigger. So you can argue maybe that was a special case for sensor networks. That's unfortunately not the case. We have some other works in Wi-Fi. That's a simplified state diagram in a Wi-Fi device, also switching between states, and also that we did some measurements here where the device moves from a disconnected state to connected state and starts to receive or send some traffic. Also we have some state changes here, and also we see here now quite a big different picture. That means here during the state change, again there's some difference between here and the two states. And another issue is here, or we discovered here, when we are already in the idle state. That means the network interface, Wi-Fi interface is idling, is active, but prepared to receive traffic. And what we see here are these spikes which have been surprising. And in this case, basically, it was just the device was just receiving some beacons from the access point. So we did not also model that, but this also shows that we have to be very careful with modeling. So observations, summary. So the energy consumption transitions have to be considered. So we have seen two examples where the transition is different from the previous and the subsequent state. Also during the state, there are several parameters which could influence the power consumption. I think it might be worth to consider both of these cases and develop appropriate models to reduce the errors we do in simulations or software-based energy estimation. Thanks.
I'm Dora Spenza. I'm a postdoc researcher at the University of Roma Sapienza. In this talk, I'm going to briefly talk about our experience in simulation and modeling of energy harvesting systems using OMNeT and GreenCastalia. A little bit of context. Energy harvesting wireless sensor networks are networks in which nodes are powered partially or completely by environmental energy sources, such as solar energy, wind energy, and so on. Energy harvesting wireless sensor networks are very promising because they can significantly extend the typical lifetime of wireless sensor network. However, the fact that the energy availability of the node is not constant over time really is a bit of challenge, and generally requires a redesign of traditional protocols. For this reason, there is an increasing need for simulation tools that can support the development and evaluation of harvesting-aware protocols. In our specific work, we focus on the Castalia simulator, which is a model for OMNeT, which is specifically designed for simulation of wireless sensor networks. From the point of view of power consumption, Castalia provides a power consumption model for the radio, which is based on state-based, and it also accounts for delay and power of state transition. However, Castalia only provides a very simple ideal battery model, and it has no support for energy harvesting. Our contribution in this context was to extend the Castalia model to also support energy harvesting system. And to this end, we developed energy subsystem module, which is briefly showing this slide. This is the general structure of the extension. The shaded area in gray represents the node level modules that are integrated in Castalia. We extended the energy model of Castalia by developing a new energy storage module, which is more generic and provides, with a higher level of abstraction, the possibility of simulating multi-source storage architecture. In particular, using this module, it's possible to simulate systems which are powered by a combination of storages, such as like supercapacitor, rechargeable batteries, and primary batteries. We also developed from scratch the support for energy harvesting by including a generic model of energy sources, such as like solar light and wind speed, and a couple of specific models for energy harvesters. The current implementation includes a simple model for a solar panel and a simple model for a wind turbine. The energy consumption mechanism of Castalia is more or less left unchanged, meaning that generic Castalia modules can act as energy consumers by sending draw power messages to the energy subsystem. The energy flow from the energy storage to the energy consumers and from the energy harvester to the consumers and the storages is handled by an active module that is the energy manager, which allows also to simulate a smart power unit. This architecture is quite flexible because it allows to simulate energy harvesting network, which are heterogeneous in terms of harvesting and storage capabilities, and also allows for having multiple energy sources in the network and multi-source cluster. GreenCastalia is released as free software. If you are interested, you can download it from the website. It's actually the current version is actually specific for Castalia, but we think it's possible to port it also in other frameworks. Okay. Thank you for that.
My name is Saeed. I come from the University of Southampton. Now I'm my final stage of my PhD. Basically, my background is this month. So this is actually one of my works in my PhD work. So you already heard about a lot of energy modeling in wireless networks, computer systems. But for my case, it's totally different. I'm talking about the energy modeling in StreetlightSim. Okay. So what our interest is, we try to actually create energy schemes that is distributed, and we use sensing to create lighting conditions that actually meets different user needs. So for example, like what we have over here. Okay. So in order to evaluate this kind of lighting schemes, we need to have a proposed solution tools that allow us to simulate and to evaluate the lighting schemes. So what we come up with is we come up with a simulation environment we call it StreetlightSim. This tool is basically built on top of a MID-SIMS, framework and Sumo as well. And we also use the bidirectional coupling module from the VANs. I think someone mentioned it before, to actually link these two simulators together. On my left, this is the GUI of the OMNeT, and the dot actually represents the location of the street lights. Different colors actually represents the different lighting levels of the street lights. Actually react based on the detected road users. The small arrow here actually is the road users, and on my left is actually the GUI of the Sumos. So, like I mentioned earlier, we're actually not modeling the energy consumption of the sensor nodes, but we're actually modeling the energy consumption of the street lights. So the tools now is in open source formats, available for downloads from our official websites. This is the overview of our tools. So you can see over here is the main thing. The majority of the module actually is built within the OMNeT Plus. Then we have the Sumo used as road users mobility trace generators based on the specific traffic profile that we actually supply. So we actually return back the mobility trace to OMNeT Plus, and we update the simulation scenarios. So what we introduced today is how we actually model the energy models or energy consumption of the street light. So because our main focus here is to create the lighting schemes, so our energy consumption of the street light is principles. We assume the energy power consumed is directly proportional to the energy levels at a specific times. For example, like if the light is being dimmed to 80%, then energy consumption also reduced to 80%, and so forth. And lately, we actually look into the solar-powered street light. So this kind of street lights, basically, you can find a lot in the rural areas, not in towns, because some of the local councils said the big panel actually is not very good for eye to see, because artistically it's not beautiful enough. So normally this kind of street light actually is used in the rural areas where access to the main power grids is not available. So what we have here is the solar power for 1, 2, 3, 5 days. So to model the energy model for the solar powered street light, we have modified energy harvested for the solar power. The alpha here actually is the random noise factors. The peak efficiency is the solar power conversion efficiency, the size of the solar panels, and the solar power reading at specific times. So this energy is harvested during the daytimes, then the energy is used during the after dark. So this is our models currently used. So far we have evaluated several lighting schemes for both grids and solar powered streetlights. So I think it's around 8 different schemes, if I'm not mistaken. And to evaluate this kind of schemes, we created energy models for lightings. It's more or less quite similar to what happened to the wireless sensor network or computer network. But we don't use any framework that provided. So it's good to have if OMNeT can have more realistic energy models for solar powered streetlights, so that we can reduce our work in terms of modeling these kind of things. We can actually focus on our initial interest. Thank you.
Our next speaker is actually going to be presenting remotely, Saeed Bastani of Lund University in Sweden. I think we will just connect the beamer here because the cable isn't long enough on the other one. Is that correct?
Yes, we can try that.
quasi PDAs downstairs.
There's a VGA there.
PDAs there.
So now let's see. Just,
Yes. All right, Saeed, we can see your slides. We can't see your face, unfortunately. Oh, we can down in the corner.
Maybe you see it on the corner, I'm not sure.
Yeah, now we see it on the corner.
Okay. Actually, I didn't hear you very clearly, and I hope that you hear me more clearly.
Yes.
We do. Yeah, the first rows can hear you, so you should try to speak up a little bit. I think in the back it's not quite so good. If people want to move forward there, they should feel free.
Okay, so let me start with my talk. I'm Saeed Bastani from Lund University, and we are here working on an energy efficient content delivery network. And actually this simulation package that we have just started working on is kind of is part of a European project which is called Convince. And this topic is closely related to this simulation package. So it is a simulation package for energy efficiency of content delivery network. Well, as I mentioned earlier, the main motivation is that we are involved in a project that which is closely related to this simulation package, and we really needed to do experiments to study the energy consumption behavior of content delivery network. But generally speaking, well, there are several motivations for other researchers to use such a simulation package as well. So it goes without saying that internet accounts for an negligible share of energy consumption, and content delivery is a major culprit that is this way. And also, CDNs are an integral part of future generation internet. So there are a lot of CDN architectures in use nowadays on the internet. With the famous one being Akamai and then Limelight and other CDN architectures. These architectures were originally designed to save bandwidth by uploading traffic. But nowadays, energy consumption of CDN becoming a hot research topic. There are numerous models, techniques, and protocol solutions are proposed by researchers. I was looking in a number of conferences yesterday that looking in this field, generally speaking, in content delivery field, there was a significant number of them, around 12, 15 conferences per year, closely related to energy consumption of content delivery in general. But the problem is that these models are just touching very specific part of the whole picture. So there is no holistic view, there is no consolidated view of seeing what is the behavior of energy consumption of a given CDN architecture. So we think that we need to create a holistic view, and we think that simulation is the most affordable way to do so. Just remind you that in this picture below, that just looking at statistics for YouTube, in 1 hour, around 3,000 hours of videos are uploaded on the YouTube only. And there are many more streaming and downloading. So content delivery is really, really important. And for our architecture, we have a reference CDN architecture to implement in OMNeT. So we call this reference architecture because most of the real-world CDN architecture can be substantiated from this reference model. So at the top of this model, we have namespace of original server where the contents are released and published. Then we have a hierarchy of content delivery servers. So at each level of this hierarchy, we have clusters of servers which are installed in data centers. So the number of levels can be as many as a user wants to implement, for example, in OMNeT. And at the bottom level of this architecture, we have user space, which includes the network of users, the devices that they use, and the applications they use to get the content. So this is our target model, our target CDN architecture that we want to implement in OMNeT. But this architecture involves a lot of different components, which we have classified into 4 components. So at the bottom level, we have internal topology, because CDN network is overlaid on the internet. So we need to have a model for internet. And fortunately, we have the basic building blocks of internet or large-scale network in OMNeT. So this might be the easiest part to implement. And then we have, on the top, we have CDN topology, it's the component including the server storage and the functionalities including content naming and access, load balancing, and content management with the caching and request routing.
Saeed, I think we're going to it would be good to wrap up quickly, and then we can go on to a larger group discussion about some of the.
Yeah, okay, so on the top of this, we have content space, which I think is the most challenging part, because at the moment there are a lot of research going on modeling the time complexity of content processing, which can be mapped to energy consumption. And then we have user space, which is actually the main consumer of this CDN.
Okay, I think we will then move on to we'll move on, because we'd like to get all the presentations in and then have a little bit more discussion how we can proceed. Radu?
Okay, yeah, that's fine.
Thank you.
Yeah, go ahead.
We just switch this one back on.
So hi everybody, I am Radu Carpa from the LIP laboratory in France, and today I will speak about something I didn't know. But I am coming very close to needing it, and hope I will do it very soon. It's bringing ECOFEN to OMNeT++. So ECOFEN, I think most of you don't know what's that. It's a module in NS3 network simulator, which allows to estimate the power consumption of a network, to model the power consumption, and also to use green functions to reduce the consumption of this network. Green functions like turning the nodes on, off, and at the same time he estimates the power needed, the power peak used at the turning on phase, and so on. It allows you to inject in the network interfaces which changes speed depending on being used at 10% and so on. So in my work, I'm a PhD student in my first year. I started by modeling a very simple network. Actually, I inject traffic in the network, and I try to reduce the network at maximum and to turn off interfaces to reduce the energy consumption. So, for example, traffic flow will change and go on a longer path, but to reduce the energy consumption. At the beginning, the model was very simple. It's just on-off. Now I'm coming to a moment when I need also the adaptive link rate, reducing the speed to 10 megabit to 100 megabits, 1 gigabit, and also energy efficient Ethernet. It's going to energy efficient mode when there is no packets to transmit. It's actually an EATF standard of 802.3AZ. So to bring the ECOFEN, which was actually done by one of my good colleagues, Saeed, to OMNeT, looking at the first moment to in INET model, it seems like everything is easy. There is the new power model in INET 3, which is used to model the power consumption of wireless networks. And there is a life cycle controller, which allows to turn interface to turn nodes on off, to control the cycle of the simulation. Now, when going to real world, and we are looking to the model, we see that wireless networks emulate this power consumption on the radio modules. The weird networks don't have this physical model. There's some work, more work to be done. More than that, actually, I thought about putting it in the traffic conditions, but it's separate. More than that, when you want to switch nodes on or off, we see that actually you can't model directly without changing what's done the consumption of a node, because nodes are not energy consumers. They can store energy, they can produce energy, but they cannot consume energy. When we're trying to switch them on, really, to do the action of switching, the life cycle controller, it's almost not implemented. It's in actual models. So what I want to, the problem which I want to raise here is that it will be a good idea to make a uniformity in this modelization. And actually, changes which I must do to implement it ECOFEN in INET are much more intrusive than I thought at the beginning. I am ready to spend the time and to implement them if this interests the community, and unfortunately I would like that it will not be confusing to the user, but the simulation at the end just hangs and generates an error, an exception, because of adding ECOFEN. Thank you.
So I think basically open up for a little bit. I guess we're running a little bit behind schedule, but the idea was just to open up for some discussion. I think we've seen that there's quite a lot of things people would like to do in OMNeT related to energy, both large-scale data centers, routing, quite a lot of existing work oriented toward batteries, actually even smart cities, where it's not so much the network that we're modeling as real things that take real power, not just computers. And so the question is, we have some kind of legacy power simulation already in INET 3. What are people's thoughts about limitations of what we have now, how we might like to go forward? Is moving things into INET the right direction? Do we want to go back a little bit more to the energy framework approach, which had kind of a standalone energy framework that could then be adopted into different communication or application-specific frameworks? So I think kind of opening it up for, so I guess that would be the direction I would be interested in seeing the discussion go, but I think anywhere the discussion would like to go would be good. Cyril, Andrash, panelists, anybody? Saeed, are you on? Can you hear us?
Yeah, I can hear you.
Okay. I guess wave or shout, or we can perhaps put you on the.
Should we switch that?
Yeah, maybe we can just switch this over again.
Or we could actually use the other one.
Is that advanced?
I think we are now technologically advanced. So I think we're going to put you up on the visual again so that we can.
Because
Okay.
This one.
Do we? Yeah, it should be. Yeah.
Okay.
So now we see your face, and in fact, why don't I turn you so that you can see the other panelists?
Thank you very much.
There you go.
Yeah, that's great.
Is that's better? Sorry for making you seasick, for turning you around all these ways. So I guess we had comments pending from Andrash.
Yeah, so
Syria?
the thing that came to my mind, perhaps inspired a little bit by the photonics work, is that it seems to me that the underlying physics should be kind of universal. So if you can develop some kind of elementary packages that kind of capture the physics of transmission, either wireless or wired, and you define some sort of interface API to expose that to a wide range of models, that seems to me to be a rather attractive avenue to pursue, rather than each particular area of modeling having to reinvent their own energy models, implementing in slightly different and probably slightly incompatible ways with everybody else.
Yes, Andras had a pending comment, and then Michael.
I'd like a quick follow-up. I mean, this is a good idea, but main important question for me is probably where should we place this more or less universal energy consumption, energy production, energy harvesting, everything that it supports thing?
I think maybe I'll ask speakers to come up and get a little bit closer to the speakerphone.
Sorry for making this not possible for you.
No, I'm sorry you weren't able to make it. So I'd say if you're going to speak, come up and at least come closer to the.
So main question would be, where should we place this overall, a huge, humongous thing that should take care of? Should it be inside INET? I would vote for more like a generic approach that would be inside OMNeT, because I think we have seen today that there are several things done in multiple communities that don't use INET, that use other frameworks, or that maybe combine different frameworks like veins and other stuff. So I can, just by imagining, there might be some ways to levitate those signal slot mechanisms, put some generic abstract INET, energy modeling, energy manager thing. So I guess Andras can comment on that.
Yes. I will start a little bit of history, that the energy framework actually has done quite a career, because it started as a standalone framework, then it was ported to different models, and actually what was in the INET framework before the 3.0 version was actually also some contorted version of the energy framework that has gone through like 3 different porting from one framework to another.
Guilty.
And what we have currently in the INET framework is a little bit of improvement, intended improvement over the energy frameworks. Once we have these life cycle controllers, which is responsible for modeling that the node boots up and it runs and it crashes and so on. And in every protocol model in the INET framework, we have to support this life cycle. What we had on your screenshot was that in the BGP model specifically, this was not implemented, and probably you can find some other protocol models which do not implement this life cycle operation. And regarding the energy side, in INET framework we have energy sources, which can be either batteries or the grid. And the battery has an abstract class interface, so we can plug in different battery models, non-linear, whatever. And we are actually in need of these models, because we don't have many of them. And then there are protocols which, in the ideal case, they publish information about what they are doing. And then we have consumption models which keep an eye on what different protocols are doing. So what is actually, for example, what a radio is doing, whether it's receiving or transmitting, and translates it into energy consumption. And then it can tell the battery to draw some amount of energy from the battery, or turn on drawing some current, turn on and off drawing some current. So this is the current state in INET, and I would be very much interested what value everyone sees in, for example, Castalia and the Pavis framework and other frameworks. So what are the good ideas that could be taken over and ported into INET? Yeah, that's it.
So what I would be very interested in seeing is whether actually it is really possible, exactly as Michael already kind of suggested, whether all of these ideas, can we take them from INET and put them into OMNeT, into the core? I know that it will be a little bit against the design of OMNeT, but on the other side, energy is for me something so ground-basing as communication itself.
Well, OMNeT can submit anything from abstract queuing networks to call centers.
I know.
And so actually it doesn't have
all
a
that
place
power.
in OMNeT core there, but it could be, you can use the energy framework actually without the rest of INET. So
That's also an
we have these INET features, and if you turn on everything else, then you're left with the energy framework. So actually this part is pretty much independent from there. This could be extracted actually if needed from INET.
Because right now it really looks like it's all of these works are extremely fragmented, and many people are using INET, but still there are some who use Castalia, who use beams. I don't know how they actually solve this problem. It would be really nice if we can stick to one, and if somebody would like to have a new model, he or she puts it directly into the whatever framework it is at the end, whether we call it the energy framework or whatever else. It would be just nice to defragment the efforts.
Yeah. Okay, like Pavis is, as I heard, it's no longer maintained. So if nobody's working on it, then probably what we could do is take the good ideas from it, or take code from it if it's open source and license permits, and migrate it to other pieces of software which is used actually and is maintained. And I'm not sure about the Castalia status. It's not very active, I think. I don't know.
Castalia is not very active. I think that everything for energy in Castalia has been improved in GreenCastalia. So I don't think there's any energy-related functionality in Castalia. Dora may be able to say more, but I don't think there's anything in Castalia that's not done as well or better than GreenCastalia. For the energy consumption. For me, the hard part isn't so much modeling the power sources. I think that's relatively straightforward because they abstract away very nicely. I think it's more how to model what module is responsible for informing the power sources and power is being used. And that's really the hard part. For a wireless device and a radio, it's totally clear. If you have a wireless device and all you care about is its radio, it's easy. It's relatively easy. It's relatively easy to say what module has the information and what module should be responsible. Because that's the only way you can keep the system modular. You can't have two things thinking that they're responsible for informing the system about energy consumption. Once you start building more complicated models of your sensors, if you start to need timing, how long is the processor turned on? How I cache data in a smartphone? My memory management in a smartphone will affect whether or not the processor can go to sleep. If you start to want to model those sorts of functionalities, everything is consuming energy, but what module is responsible for that kind of information? And I think that's really the hard part, especially when you start to want to be more heterogeneous, wireless, wired, larger networks. We have Levante and...
Just a short comment on that. And from the energy framework's point of view, they're just consumers. I mean, what if you separate the consumption model from the actual thing that is doing the work? In that case, you could have different kinds of implementations. I mean, you could have a consumer model which is more complicated and takes into account the actual hits of the signal, or it just relies on the state of the radio, whatever. I mean, if you separate the consumer from the rest of the system, the consumer module, I mean the module which tells the battery or the energy storage, the amount of consumption, then I think it's flexible enough.
If you want to maybe come forward so that you can speak to the phone.
Oh, okay.
I guess the question is that for some models, I may only want to represent things at the application layer. I may want to say, I'm not paying too much attention to the details of the radio. And so then it's the only thing that knows what's generating the traffic, perhaps, is an application layer or a higher layer module. And then I may want to study the same sort of system, but have a much more detailed radio model. And now it's the radio model that's tracking radio states. And if I have these sort of heterogeneous systems, which module is supposed to take responsibility? And I'm not, perhaps you could say more how you think a consumer could track throughout the stack which should be responsible.
That's a model called...
I have a point to make here.
Yeah, why don't you go ahead, since you don't have all the feedback from...
Yeah, actually, you raised a very good point about the radio modules responsible for this energy power consumption. And you also mentioned that which module should be responsible for different parts that energy is consumed. I just wanted to remind you that there was a recent work by Bianchi. I don't know if you have heard of Bianchi. He's one of the very big figures in the field of 802.11. So they had a very good study, specifically an empirical study that's showing that the transmission is actually not necessarily the dominant part of energy consumption, but the energy is mainly consumed in the different protocol stacks. So, for example, in the MAC layer, and also in the management layer, and also on the top layers as well. So, I think roughly to answer your question, I think each module on the way on the protocol stack, where a packet is passing, should take some part in measuring the energy that is consumed directly in that layer of the protocol stack. And there are models as well. So now, as I mentioned in Bianchi's model, they have a model telling you, considering everything into account. I mean, the different contributions from different layers of the protocol stack, and as well as the radio interface in itself, and also with transmissions and everything into account. So they have proposed a model that I think working very well, at least according to their experts. So I think it's good also to look at those recent work, empirical works, and see how they can be incorporated in the audience.
Okay, so we had a follow-up from Andras, and then Jörg, and then the panelists want to perhaps say something.
Sorry.
You had a quick follow-up?
Yes.
Yeah.
So it's a very good point that all protocols and all modules like the radio module are responsible for energy consumption. But if you look at a situation that, for example, a radio or a MAC model or TCP model, IP model, they model abstract things. And if you look at real hardware, there's behind that there are different hardwares from different manufacturers, different processors at different clock speeds and so on. So they're going to have
different characteristics regarding power consumption. So I'm telling that if we want to model power consumption, for example, by the IP stack, we don't want to put that code into the code of the TCP model or the IP model. We have to decouple it.
We have to
Yes.
decouple it.
And put it into some energy consumption model, which is modified by different blocks what they are doing, and that translates it into energy consumption.
That's what I was referring to.
Levanter was the implemented the current energy.
I think the issue is how much in different scenarios, how much of the protocol stack are you actually instantiating for a given simulation, which I think can be a little bit of an issue. At some point, you want to go to, so let's simulate all of the hardware completely and then just only model the energy consumption in the hardware, and that's not, I think, necessarily scalable.
Okay. So my opinion from the side of the Pavis framework, because I think I'm using the most time, is you have to, and the responsibility, which module has to track the power consumption. So we came to the conclusion that the hardware models, for example, we modeled the radio transceiver with the different states. Also, Torsten showed a very good slide. If you miss the calibration state, if you miss the error state, you're totally messed up with the simulation results. We started our measurement equipment and we had mismatch 100%, 200% between simulation and real world. So we got into the hardware models of the transceiver. We had to fine tune them, we had to model the different states, and then we come now to about 3 to 5% mismatch between simulation and real world measurements. That's the radio transceiver. The other thing is the IP stack. So the timing behavior of the firmware, of the software running. We came to the conclusion we have to do a similar approach as the CUJA simulator does. You have to write your code and you have to fetch the timing information and put it into the code. And then we have a hardware module of the CPU. There are also different states. And so to say, the hardware module is responsible of the energy consumption of the states, but the timing comes into play from the firmware. And that's also the approach which is implemented in the Pavis framework. So the Pavis framework gives you the infrastructure to model your hardware, but you have to do the hardware modeling by yourself for different microcontrollers, different radio transceivers, as Antosh mentioned. So that's our approach. The problem is the scalability. So if you want to provide several modules, of course it's a cumbersome thing, but it was the only way to bring simulation to the real world, which was shown by our machines.
Anna, and then maybe we can hear from some of the people who look at wired networks a little bit also.
I think it is very important to keep in mind really the credibility of the data framework at the end, whatever we call it later. Because if we're trying to go only for scalability and try to solve this problem in the first place, we might really hurt the credibility. The approach Pavis has taken, I kind of tend to say this is the better approach, because it's just more credible approach, and you make sure that even people who are not very well aware of what is going on behind the scenes, they can actually use it in a credible way, instead of playing with some numbers and measuring only part of an IP stack and falling out everything else just because they don't really grasp it, or because it looks better, or whatever else. So it's important really to keep in mind that there is the hardware which actually uses the energy, and the software which controls the hardware, but the software by itself does not use energy. So to me it's very important to make the step through the hardware. Even if it's not extremely scalable, even if you have to go for your own configuration, still you can simplify there and say, okay, we have a sample configuration, hardware configuration, which works. Like in most of our networks, there is something like a standard configuration.
I think for the wireless case, something like Pavis works, but perhaps some of the people who look at data centers or larger networks where the device, modeling a little Kontiki device is not that hard. modeling a smartphone even is quite hard.
I'm actually talking more in terms of smartphones.
Yes, modeling a smartphone still has some challenges, and then modeling the kind of hardware, perhaps, that you're looking at for routers, modeling for data centers.
Yes, think about cloud computing
Yeah.
infrastructures. I think that's probably a field maybe to be supported. Maybe,
Definitely.
and that's
Absolutely.
maybe something.
And I'm not sure the hardware model.
I don't see something that changes dramatically just because we have bigger infrastructure, or I mean the concept is the same. There is the software which uses the hardware which uses energy. And if you skip some part of it, you definitely hurt the credibility.
I think the energy modeling should not be somehow limited to communication issues.
Also, exactly, we have been thinking about putting, for example, sensors into OMNeT for a very long time. We haven't done anything there, but I imagine that at some point it will drop out from somewhere. Or the environment by itself, and this is also very important. Keep in mind. It's all
So I think, Cyril, I think we're running close to coffee break time.
We're already like half an hour over.
But Michael still has another comment, or?
No,
You
just my comment. The series is just organizing
So I'd
something.
like to thank all of the organizers. I wish the students good luck. People with projects also, good luck moving forward. I think this is a topic that's important for the community, and
thanks to you, Laura, for organizing that.
Yeah.
so I thank everybody.